It's time to think about moments in virtual work. So from prior lessons, we know that the reaction forces are half the load, since the load is halfway between points A and B. Okay, the change in work is moment times d theta, which is L times y, a moment about B. We'll calculate the moment about point B. L times y minus 1/2 P, L over 2, excuse me, L over 2 P times d theta. So AY equals P over 2, just like previous lessons. So far, no advantage to virtual work. Now, you'll notice the sign conventions aren't followed. LAY is clockwise. Normally, we consider that negative. It doesn't really matter because we're going to set the virtual work equal to 0. So here's a few examples of more complicated problems where we can analyze things with virtual work. Here's the scissor jack type of problems. Let's think about this problem here. So you have two linkages right here, 1 meter each, 1 degree of freedom. Theta determines everything. So the y position is going to be 1/2 meter sine theta for both the coordinates, by the way, for both of the weights, for both the weights of the linkages. The mass is 10 kilograms, which makes it 98.1 newtons. The x coordinate is going to be twice the linkage times cosine theta. So let's go to the next slide. And we get the x coordinate here. Twice the linkage, 1 meter cosine theta. Okay. Find the delta. -2 sine theta. Delta theta. Y. 1/2 sine theta. So that's 1/2 meter sine theta is how far it's down. Take the deltas. So that makes it 1/2 meter cosine theta delta theta. Increasing theta will cause a decrease in x and y, and increase in y. Okay, so what we get in this equation, delta U has to equal 0. So weight times delta y, that's the weight of each link times delta y. Weight of each link times delta y. Force times delta x, the applied force, 25 newtons applied force. So on the previous slide, you saw the delta y was 1/2 cosine theta d theta. So this expresses those first two terms in the equation above. In the previous slide, we saw that delta x is -2 sine theta d theta. So now we can get an expression in terms of tangent. And that's exactly what we do. We crunch the numbers, we do the math, and we get this number. So if we had used equilibrium, we would have had lots of work. So we've eliminated some tasks. so that we get the answer quickly. That's the point of virtual work. We can get to answers quickly. Let's think about this example. So we want to know what is the force P to maintain the equilibrium at angle equals 60, and here's theta over here. Here it is on the diagram. Unstretched length, theta equals 30. Don't worry about the mass. So only the spring force and the applied force do work. When you put a load on it, a P, you get a length. The stretching is 0.3 sine theta, right here, 0.3 sine theta, minus 0.3 sine 30 degrees. So that the spring force, so that's what we're calculating here, spring force equals 1500 sine theta minus 750 newtons. Now, what happens next? Delta x sub d. We're measuring from point A, and we want to know when you change theta, so you're going to have a change of distance here. You're going to have twice the change of distance here between B and P. So x sub b, there we go, 0.3 sine theta, and x sub d then is 3 times that. Differentiating, we get delta x sub b is let's go with the delta x sub d. That's the one we care about. Force times displacement, 0.9 cosine theta d theta. Let's see, force of the spring will depend on x sub b, delta x sub b, 0.3 cosine theta d theta. So let's go to the next slide. So now we get delta u equals 0, and that's going to equal negative spring force, delta xb, plus the applied force, delta xd. Well, here's xb and xd. Delta xb right here, delta xd right here. P, there it is, that's what we're trying to find. A couple slides ago, we figured this out. The spring force is 1500 sine theta minus 750. Crunching the math, we get the load equals 500 sine theta minus 250. We want theta equals 60. Sine theta is like 0.866, excuse me, and that would make the load equal this, 183 newtons. So that's the answer for this